Hey everyone. My name is Horsefax and I work on Farcaster. I'm here today to talk about building embeddable Ethereum apps using Farcaster frames. So Farcaster is a decentralized programmable social network built on top of Ethereum. And this is what it looks like right now. It's basically a feed-focused short text social network. You can create a profile, you can follow people and topics you're interested in, post things like text, images, links, and video. It looks a lot like Twitter, but it's purple. And if you squint, it might look a little bit like Instagram or Facebook or Reddit too, because it's built on most of the same social primitives. Things like your identity, your social graph, and text and media content. Just curious, like how many folks here are on Farcaster? Okay. How many are like daily active users of Farcaster? Cool. And how many of you have built a frame already? Okay, cool. So yeah, at Farcaster, we're building social networking as an open protocol. That means that your account and identity live on-chain as something that you actually meaningfully own. It means that your data and social graph are stored and replicated on an open peer-to-peer network that can't be shut down like a private API. And it means that Farcaster clients are something we design and build with programmability in mind so that you can build and distribute apps permissionlessly. So David actually already gave us a really great intro to frames and what they are. But I'll give you another. Frames are a way to build interactive apps that are embedded directly in the Farcaster social feed. So here's an example, and this is kind of the demo we'll be using today, which is a little game called Yoink. If you're building an Ethereum app, it can be pretty difficult to get that app in front of users. They have to find your app on the web or on social media. They have to click through to the app, open a new page, connect their wallets, sign in, and only then can they do something interesting. I think most builders in this space have had this experience. It's like, can be really hard if you've built something just to get it in front of users who have a connected Ethereum wallet. So frames help solve this problem by helping your app get distribution. They enable you to embed interactive calls to action and Ethereum transactions directly in the Farcaster social feed so you can reach users where they are. We have right now around 50,000 daily active users on Farcaster, and creating a frame is a great way to reach them. We wrote the first frame spec back in January, and since then developers have built thousands of frames for all kinds of interesting applications. So apps like Rodeo, Zora, and MoshiCam have built frames that enable you to mint and collect in feed. On Farcaster, every polymarket link is a frame where you can make a prediction in just a few taps. Every mirror and paragraph article is a frame where you can subscribe in one click or even launch a mini app to read articles right in the app. Yeah, let's let that one play for a sec. So yeah, you can open, click through to open this mini app and actually browse an article directly in Warpcast. There are frame apps for organizing and managing events that take place in the real world and events that are online, things like meetups and audio spaces. Developers have built frames that facilitate payments, subscriptions, and commerce. And that's just the surface. There's a lot more. Things like polls, media, games, crowdfunding, tipping, swapping, and much more. So if you want to explore frames for yourself, a really good place to find some is this Explore tab in Warpcast. If you tap this globe right in the center of the nav bar and scroll down in Warpcast, you'll find sort of an interactive screen here where you can browse through not just frames, but apps and other things that are built on top of the Farcaster protocol. So frames are cool on their own, just as like an embed that appears in the feed, but they get even more interesting when you combine them with other programmable surfaces in Farcaster. So sort of throughout Farcaster, we've tried to build in places where you can program Farcaster, right? You can build through using APIs and using open standards the ability to build your app into the Farcaster social feed. So for example, developers can build mini apps that interactively add frames from the cast composer. So you can create a poll with Ponder and insert it into a cast on Warpcast. You could search for a GIF to insert from a GIF keyboard, or you could share media like books, songs, and movies with Nook. You can also launch a frame by clicking on a cast to take actions like translating, bookmarking, and tipping that exist in kind of the context of a cast. So you can think of this almost like a browser extension for a social network or a programmable like button that's built into the app. A final way you can use frames is sending them in direct messages. So like this event reminder on the left was sent through a direct message. So sort of closing this feedback loop where you can communicate back to the user and send them a frame in a direct message. So we think about frames, actions, mini apps, direct messages, all of these things as developer Legos that we're building on top of Farcaster and into Farcaster clients. And building Legos that enable you to kind of snap them together to extend clients in new and interesting ways and embed your app throughout the social feed. Frames are not just on Farcaster. They originated on Farcaster, but ultimately they're based on a pretty simple open spec that anyone can implement. And in fact, David and OpenFrames have extended Farcaster frames to be usable in a bunch of different applications throughout the ecosystem. So thanks to projects like OpenFrames, you can build frames that now work across Farcaster, Lens, XMTP, the open web, and even like you demoed using their extension on X. We think there are now at least 24 apps that display frames across the Ethereum ecosystem. You can see some of them here. On the left here as well, you can see a frame that's embedded in Lens, so a math quiz frame that works across the Farcaster and Lens ecosystem. Okay, so we're going to build a frame in today's talk. Let's talk a little bit about kind of the theory behind frames and how they work. Ultimately, they're based on a few old, reliable web standards. The three big ones are Open Graph, HTML, and HTTP. So one thing I think is great about frames is that if you can build a web app, you can build a frame. In particular, I think they're cool because they're permissionless, meaning anyone can build one. They're simple, which also means anyone can build one. And we've seen lots of developers come to Farcaster and kind of build a frame as their first app, right, or their introduction to web programming or Ethereum programming. And in fact, they're so simple you might call them extremely constrained, but I think that encourages creativity. So if you've ever copy-pasted a link from the web and seen it unfurl into a preview image, this was probably thanks to Open Graph. And here's a great example, right? If you copy a GitHub repo URL and paste it into Twitter, you get an image that looks like this. It's this nice dynamic image that shows the repo name, icon, number of stars, and forks. So it's possible for Twitter clients and applications on the web to render this because GitHub includes special metadata tags in the HTML head element of this page. And in fact, here's what they look like. These meta tags describe the image here, the type of the content. Here, this is a website. The title, description of the site, and a URL. So when you post your tweet, Twitter makes an HTTP request to fetch this page, loads the HTML, looks for the head element, parses these metadata tags out of it, and then ultimately renders this really nice image instead of the plain URL. So Open Graph is actually kind of an old-ish standard at this point. It was created way back in 2010 by Facebook, but it's still very widely used around the web. And in fact, you might have seen more of these dynamic images around the web lately. If you use Vercel, they have really good tools like Satori, which are used for rendering HTML into a nice dynamic image. And in fact, one of our inspirations for frames was the fact that we were already rendering these share images for Farcaster casts. You can like click within Warpcast and share out an image, and we'll render this share image that you can post around the web. We realized kind of by building this that there were pretty good tooling out there for rendering JSX, rendering HTML to images, and so it's kind of becoming possible to turn Open Graph previews into these simple, if constrained, UIs. Okay, So the big idea behind frames is that we're going to take the sort of static Open Graph metadata and extend it with the ability to define interactive actions and simple UI elements along with static components that you're used to from Open Graph, like an image. But ultimately, it's all the same basic idea. Farcaster client will fetch the URL. It will load the HTML, parse out the meta tags, and render an interactive embed. It's just that if it's a frame, we have happened to add these buttons and actions that define some interactive things you can do with it. So here's what frame metadata looks like. You can see it looks a lot like Open Graph. You can define an image. Think of this as your UI, right? This is kind of your browser canvas in which you're going to build and render your application. You can define simple UI elements. So buttons, you have up to 4 buttons. And you can add a very simple text input. That's it. And then finally, you can define a web server, which is how your frame handles interactive actions over HTTP. So it's kind of like if Open Graph was created by cool Mark Zuckerberg. That did not land. All right. Cool. Okay. So here's how a frame interacts with the server, like kind of the whole life cycle more concretely. We've got the cast composer up here. This is where you're typing in your cast, your post. So yeah, when you first post a link, your Farcaster client will get the URL. The frame server then returns an HTML page, right? This defines those images, buttons, and actions in the markup. The client parses that frame metadata and renders it in feed. So it looks like this. Frame server returns frame metadata, the client parses that and renders it. So clients will typically cache this initial frame. In fact, in Warpcast, they're like cached quite heavily, so we can build feeds and render them quickly, which is kind of a common frame gotcha. So be careful about this in that your layout and your initial image will typically be cached. Okay, so now when the user comes and clicks a button, the client makes a post request to the server. And this post request includes some information about which button was clicked and the user's identity. From there, the server can return HTML that defines another frame. And if there's a button to click in that frame, the client posts back to the server. It can return another frame, so on and so forth, sort of just back and forth HTTP request response cycle. So this means you can chain frames together to create workflows that have multiple steps. You can branch based on user input, return frame A if this, return frame B if that. And you can even compose frames, kind of like you might compose functions. You can have one frame make a request to another. Okay, action types. So you can define this image, you can define these buttons that make particular requests that represent different types of actions. What are those types of actions? So there are a few different ones. By default, clicking a button will make a post request to your frame server, sort of standard HTTP post. There are some other types as well. So you may want to link out, right? Send the user to an external link. You can do that using either a post redirect button or a link button. So which is one of those is a sort of a dynamic link where your server will receive a post request. You can respond with a URL that will redirect the user to. So you can use that to kind of figure out if you want to dynamically link based on some state of the request or the user or whatever. Versus a link, if you just want to add a static link, which is like a pretty common typical use case, you can simply add that as a link button. And then the most interesting one, and the one that we're going to talk about a lot today, are transactions, which make a request to fetch an Ethereum transaction. They get the call data for that Ethereum transaction, and then they forward that to the user's connected wallet. So you can use that to basically embed direct Ethereum transactions, calls to action, directly into a button on a frame. Okay, so images and buttons in HTML metadata, you can think of these as defining your frame UI. We have HTTP requests made to your frame server that define the actions you can take, the behavior. There's one more really important frames concept to cover, which is the signed frame message. So this is the data payload that the client posts whenever you click a frame button. And this is a JSON object that looks like this. It's compact, but it actually communicates a bunch of useful information to your frame server. So up here you get the Farcaster user ID of who interacted with the frame. In this case it was me, that's my FID 361. It tells you what frame they interacted with and when they did it. You get in here in this cast ID component information about the cast, the post where the frame was embedded. And that includes who posted that cast, which is very useful. And then, of course, you get which button the user pressed. So you can use this to figure out what they did and then respond to it on your server. So in addition to all this, since Farcaster data is open and public, you can further enhance this with data from the user's social graph or on-chain history. So for example, you could look up whether the user who interacted with the frame is following you, or you could look up their linked Ethereum addresses and figure out whether they own a token, things like that. This last component of the message is probably the most important. So this trusted data field is a hex-encoded cryptographic signature that you can use to verify the data in the rest of the message. So every post, follow, and like on Farcaster is a cryptographically signed message, which is stored on Farcaster hubs. When you publish a cast, basically you're signing a message with an ED25519 key. Hubs will store that message as long as the key exists in an on-chain registry. So your Ethereum account controls your identity. That account can delegate to an ED25519 key, which signs your messages on the protocol. Those go onto Hubs, this peer-to-peer network, which stores all the data. Yeah, this is kind of a diagram of the hub system and how hubs work. So a hub will accept a message if the cryptographic signature is valid and if the key is in the on-chain registry. So frame messages use this same format, which we use for signing posts, signing reactions, signing all the other types of messaging data on Farcaster. You can verify them in exactly the same way, but they're ephemeral. So they're not stored on the network, but you can still verify them in the same way. So this means it's possible to build authenticated experiences that rely on the user's identity. And you can do this permissionlessly without needing an API key or asking the user to log in. And so concretely, the way that you can do this is to interact with an HTTP API that's exposed on the hubs. You can basically grab that grab that hex-encoded signature out of the message data, make a request to a hub API, which will verify it for you. And if you want to do that, trustlessly as well, you could verify the signature yourself, check the on-chain signature, et cetera. And that's it. So frames are HTML markup that describes an image and buttons. They are HTTP requests back and forth to a web server. And they're assigned data payload. Those are the three most important principles. OK, so some design principles for building good frames. I think we've seen thousands of frames built over the past year, and after seeing lots of experiments in the wild, there are a few principles that I'd encourage for building good frames. The most important is to just keep them simple, fast, and focused. The very best frames have a clear call to action and a linear workflow with only 1 or 2 steps. So if you're trying to build like a complex multi-step app that has a lot of branching and error handling and callbacks, a frame might not be the best way to build your app. They're really good for simple calls to action, linear workflows without too much branching. I like to think of a frame kind of as a Game Boy, right? It's this very simple constrained user interface. You have a couple buttons, and you want to fit sort of a simple, fun, fast experience into a very limited UI. Or even better, think of like the Wii U, if you remember this. Think of it as the little gamepad screen that was built into the Wii U. Basically, there's a whole game, your application, that's going on outside your frame. But your frame is a way that you can highlight a specific action in context in the feed and encourage somebody to take an action in context now. You can definitely build your app frame first if you want. And frames are permissionless open standards, so you can do whatever you want with them. But I think it's almost always best to keep them simple. Here are a couple examples I grabbed that I think are good frames. This one is from Hypersub, which is a subscription service. And what I really like about this one is that it has a very clear CTA, just has a single button, and it has really good default settings. So you can see, well, Yeah, you can see by default it will subscribe you to a single month. So you can ask the user for kind of complex input, but by default it is doing something with a good default. So yeah, this frame has a really simple, straightforward, single-click workflow. You send the transaction, and it shows you the receipt right away. That's it. So I think this is a great way to bring a really simple call to action directly into the feed. Here's another one. This one's from Zora. I like this because it has one very clear in-feed action, mint, and it includes a link out to the main app if you want to do more. So don't think of the frame as your entire app kind of crammed into the social feed, into this very constrained UI that we provide with frames. Think of how you can bring the most important actions from your app that exists outside of Farcaster into the frame and kind of put those in front of people. So Zora also really makes nice use of the image. They're showing the number of mints and comments dynamically. This can be kind of tricky to get right because of the way frames are cached, but we will respect cache headers, and you can build dynamic frames that kind of regularly update and show things like the number of people who have minted, the number of people who have interacted. Yeah, I'd describe this as kind of an advanced technique, so practice a bit with frames before you do this, but it's a great technique if you're careful about how to do it. So Paradigm put together a great resource called the Frame Interface Guidelines, which has a bunch of principles for building good frames. If you're interested in expanding on this, I would encourage folks to go check that out. So there's a Figma guide and a bunch of guidelines here for how to think about building UI and how to think about building really good user interactions in frames. Okay, a few common gotchas. Frames in general are really simple. I think there are a few common difficulties and gotchas that we see with lots of people who build them. And the three big ones are performance, large images, and caching. So first up, performance. Frames need to respond in less than 5 seconds or they'll time out. And especially if you're using a serverless tool that might have a cold start, this can be kind of difficult sometimes to fit your app within this timeout. So ideally, you should cache and index as much data as you can. You should add loading frames like interstitial states if necessary, if you're loading a transaction and waiting to load the hash or looking at the status of a transaction on chain. And yeah, if you're using something like Vercel, a serverless deployment where you might have a cold start, be careful to try to keep that warm and keep that as responsive as possible. The second common gotcha is large images. So we do enforce a 10 megabyte limit on image size. If you're not careful, you can exceed that easily. The other sort of more subtle but common gotcha here is building very complex user interfaces using some of the main frame frameworks. So Frog and Frames.js, which are the two main frame libraries, can have trouble rendering very complicated JSX that has a lot of components. Third pretty common gotcha is caching. So your initial frame will always be cached by clients, and that initial image will be cached according to whatever cache headers you send down to the client. So it's possible to build frames with dynamic images, but it can be tricky to get right. Fortunately, there are good tools for testing this out. So Warpcast provides a frame validator tool that can show you your cache headers. We're going to look at the Frames.js debugger as well when we build out this frame shortly. So those are good ways to kind of experiment with and watch these gotchas. Above all, though, with all three of these, I think just keep it simple. Keep your images simple. Keep your applications simple. Try to think about what is the one action that you want to bring in the feed if you're building a frame. Okay, so that's theory of frames. We're going to try and build something here. Let's move over to doing some live coding. Frames are simple enough that you can use any web framework to build them if you like. But today we're going to use Frames.js, which is a library and tool for building frames in JavaScript and TypeScript that works on top of a bunch of different web frameworks. In this example, we're going to use TypeScript, Next.js, and React today, but it plugs into a bunch of different frameworks, and so you can sort of use it with your tools of choice. We're also going to use a few ecosystem tools. So we'll use VM to read and interact with a smart contract. We're going to use Nanar, which is a Farcaster API service to enhance our app with Farcaster social data. And we're going to use Ponder, which is an indexing tool for Ethereum contracts. Okay, yeah, and the goal today is to build a really simple game that interacts with a smart contract. It's a capture the flag game called Yoink. Here's what it looks like. So in Yoink, you can see who currently has the flag. You can yoink the flag from them, and when you yoink it, you will get a token in your wallet. So we'll track the number of yoinks that have happened to build a leaderboard, and then we will enhance the context of the game with Farcaster data. All right, hopefully this goes well. I'm going to switch over to live coding from here. But if you want to follow along, you can clone this repo from GitHub to get up and running. And yeah, let's give it maybe 5 minutes for folks to grab this repo and get set up if they want. In the meantime, maybe we can take questions. All right, we'll give it like 30 more seconds, then I'm going to switch over. Here, I'll put it back up for a sec. Yeah, github.com/horsefacts/yoinkdevcon. I can maybe cast it out on Farcaster too if you're following me. Let's do that. Cool. All right, praying that the network holds up here. Okay, so yeah, here's our Yoink repo. This is our frames.js repo. This has been created with just like the frames.js starter kit. We'll give a quick walk through the repo here. Okay, so if you pulled it, you'll want to just run yarn to install dependencies, and then you can run yarn dev to spin up the frames.js debugger and test server. We'll look at this frames.js debugger in a sec, but let's take a quick look at how this is all laid out first. Okay, so if you've used Next, you'll see like this is the structure of a pretty typical Next app. We have stuff here in app, which will define routes within our application. We have some components, a frames folder here, which will create a /frames route. And then we have this global stuff like our global layout and our home page. We've based this on the frames.js starter kit, which has this really, really useful set of examples out of the box. So if you look in this folder here, examples, you'll see sort of worked examples for lots of interesting and different things you might want to do with frames. So here's like the most basic frame, caching, building composer actions, dynamic routes, error handling. So if you're poking around in this repo sort of as we go, this is a really good resource to go look at how to do different things with frames. So basic structure of our app here, we have the home page. And then nested inside this frames directory, we'll have our actual frames code. And we can go look at this home page. Over HTTP. Cool. So you can see here, if we look in our page markup, we're serving these meta tags, right, that we looked at: FC frame image, open graph image, and our frame buttons from this entry point of our app. Unfortunately, Frames.js takes care of injecting this into our homepage and everything for us. We can just work on building the frames using the tools that it's provided here in this frames directory. Okay, so let's look at Yoink from the top, and then we'll kind of roll back and build it out step by step. Here in this frames.ts file, we're kind of defining the configuration for our frames application. So a base path, which is like where we're going to mount the frames. We can define sort of all the configuration for the app here. Go check out the frames.js docs for all the details on how this works. We can define things like middlewares. So if we wanted this to be compatible with other frame ecosystems, like Lens or XNMTP, we could add middlewares here that extend it to be compatible with other ecosystems. And then here's our entry point frame route. So frames route.tsx. And you can see we're kind of mirroring that structure that we looked at in the frame meta tags. We can define an image and some buttons. And the cool thing about Frames.js is that we can define this image dynamically using JSX. So if you're familiar with writing React, you can build up a dynamic image here just by using JSX components. We can also use Tailwind styles in here. So you can see we have like flex column, font bold, text 8XL, all of these Tailwind identifiers. You can use these to style your frames as you're developing them. So here's our simple entry point image. It says yoink. Click to yoink the flag. We have a button. And this button points to another frame. It's pointing to this path @/start. So you can see we're going to build out a few different components here, a few different routes within the frames. You can think of sort of each of these subdirectories as a separate frame. So here's the start frame. When you click this button, it's going to post to the start frame. And we're going to want to define a route handler to handle that. Here's this frame. OK, so yeah, let's just step through this in the frames debugger. So when you run yarn dev, this will spin up this local frames.js debugger, which you can use to browse and view your frame. This provides a bunch of really useful information about your frame. You can see some diagnostics around the tags. You can browse your console. You can see the meta tags. And then you can sort of step through your frame step by step here. So we'll click start. Oof, OK. Network connection is working. It's going to show us who currently has the flag. We'll do a transaction here. I've yoinked the flag. I can click an external link here to go view that transaction on base scan. And then we've got a simple leaderboard here that shows who has yoinked the flag, their addresses, and how many times. OK, so that's the idea. Let's go through and build this up step by step. OK, so we're back to the frames.js starter here. We have kind of a simple demo app where we can increment and decrement a counter. Let's start by just building like the start page for our frame. So we'll come in here to our entry point route. Let's just define some simple text in here. Yoink. We'll remove this text input, remove these buttons. And for now, we'll just put a simple button here that thank you. Yep. OK, so this is just a simple button that points back to the initial frame. So to start, this is not going to do anything. Cool. OK, so there's our image. Yoink, click to yoink the flag. We have a button. We can click to start. This is just like posting back to our same initial frame, so it's not yet doing anything. So if we wanted to, we could access the context from this request. So that information that's in that signed frame message in this context object. So we could show, for example, which button was pressed. Or the ID of the user who pressed it. So we'll just put those here in this initial frame. Cool. So you can see, right, there's no value here in this initial request, because that's just the GET request that loads the initial frame. Once I press the button, it receives that signed payload, including information about who's interacting with it. And we can embed that information into the frame. So you could build an entire app with like a single frame route if you want, doing your switching and branching within a single route, just like posting back to one route if you want. I think there are a couple examples, like the simple examples in frames.js do this. But if you're building an app with like more than one workflow, for me at least, it makes sense to kind of separate these out into individual routes for every single frame. So we'll kind of define one API route or one frame API route for each frame. So in this case, let's create a start route. And we're going to, when we push this button, we will send the request to the start frame. All right, so we'll create a directory in here with a route.tsx. I'm just going to copy paste our start frame. And let's just change the text on this frame. OK. We need to update this one to point to this new route. Cool. Let's remove this context data. Cool. So we've got our initial frame, right, our entry point. We're posting and sort of, you can think of it as returning a new frame or kind of redirecting to the next frame that's going to handle the next step in the workflow. So with Yoink, it would be really cool to use like a dynamic image that shows the number of Yoinks on the first image and shows a bunch of contextual information. That's kind of difficult to do in our demo and difficult to do with caching. So we're going to adopt this pattern where there's always a start button. We're going to load some data dynamically into that second step and display it in that second step. So if you're building frames and want to avoid some of these issues with caching, it's not a bad idea to sort of always start with this start step, this initial interaction, and you can start loading dynamically data from there. It's a lot easier to avoid issues that you might bump into with caching. So we'll follow that approach here. OK, so in the second frame, ideally we'd like to show some on-chain state about the game. Right, we're going to want to show the current user who has the flag, like the number of yoinks that have happened in the game. And to do that, we're going to need to read some of that on-chain state from the contract. We can do a super quick tour of the Yoink contract. This is not a Solidity workshop, but we can take a quick look at it. So here's how the game of Yoink works. It is a ERC1155 token with some special logic in here for managing the game. And we're going to transfer some different tokens to people when different actions happen in the game. So we're tracking the total number of yoinks in the game, the time it was last yoinked at, the current record for most yoinks, the address of the top yoinker, and the address of the person who last yoinked the flag. Everyone has a score stored in this mapping. And then here are the rules of yoink. So you can't yoink the flag from yourself if you already have it. We also will enforce a cooldown where you can only yoink the flag once every 10 minutes. When you yoink the flag, we will transfer you this special flag token. Also, the first time you participate, we will mint you a score token. This will show your score in your wallet. And then if you happen to be the top yoinker at any given time, we'll send you this trophy token. So we'll do some calculation on chain to calculate how long you've held the token, or how long you've held on the flag. We'll build a leaderboard, right? So track how long you've held it, how many times you've yoinked it, who is the current top yoinker, and how many times the flag has been yoinked. We have some helper functions in here for generating on-chain SVGs. So these tokens have a nice little on-chain image. Okay, we have a lot of helper code for generating the on-chain SVGs. And then the flag and trophy are special tokens, so they're soul-bound, they're non-transferable, right? So if you've been issued these tokens, we're going to revert if you try to transfer them to somebody else. So only the game can transfer these tokens. You'll get the flag sent to you basically by the game contract when you yoink it. Okay, so that's the game of yoink. This contract is deployed on-chain on base. Okay, we'll give up on that. But yeah, it's deployed on-chain on base, and we can, you could interact on Etherscan, right? You could go to basescan and call the yoink function to play the game. Okay, so let's set up to actually read some data from this contract in our frame. And to do this, we'll use VM. I'm going to add some helpers in here. Oh, here we are. We're back. All right, no. Okay, so we'll grab the contract ABI. Let's add it here. And let's get the contract address. Cool. All right, and in order to interact with it using VM, we're going to create a public client here. Connect it to base, and we'll use the HTTP transport by default. Okay, so yeah, let's start by showing how many times the flag has been yoinked. We'll just create a function here, get yoink count. And we'll read our contract. And we'll call this function, I think it's total yoinks. I need to crib from my notes here, hold on. function name. All right. Cool. So that should be what we need to go read data from the contract on chain. Let's go back to our frame handler here. And before we render the image, right, we can call that function to read some data. Okay, so that's going to return total yoinks as a big int. We'll want to convert that. Let's do that in the function. Oh yeah, we need to await it too and return it. God, I love live coding. So we'll just convert it to number there and return it. All right, let's put it all together. Cool. Ugly, but there we go. Flag has been yoinked 7 times. So we're reading that state out of the on-chain contract. So next we'd like to show who currently is holding the flag. We can add a similar function here. Okay, gotta go look at what this says. Okay, this is the last yoinked by address, so this will show us who is currently holding onto it. And we can just return this directly because it's going to return an address. Yeah, cool. Cool. Okay, so we're showing the address of the user who is currently yoinked the flag and the number of times it's been yoinked. So yeah, our UI kind of ends here, right? We're not doing anything after this point. Let's do 2 things. Let's add a back button. So you can go back to the initial state. Cool. So now we can kind of go back and forth between the launch frame and this data frame, this start frame. That's pretty boring though. What we actually want to do is be able to trigger a transaction here, right, to yoink the flag. So far we've been using post actions, right? Sort of the standard action is just a post. Now we're going to use a new type of action, which is a transaction action. So I'll change this here to TX. And post actions are very simple. It's just a request response. Transaction actions are a little bit more complicated because they do two things. They need to load your transaction data. They forward that to the user's wallet. Then they get back a transaction hash, and then they post that back to your frame. So there's sort of more of a back and forth. There are two steps in a transaction. So we actually need two routes when we build a transaction. One that returns the transaction call data, and one that kind of handles the next step in the frame workflow. So the target of this transaction action is going to return the call data, and then the post URL is going to be the action that handles the response. Let's call this receipt. All right, so two new routes. Let's go create those. We'll just put a simple placeholder in here for the receipt. Okay, and then this TX data handler is going to look a little bit different because it's returning JSON about an encoded transaction. And in fact, I'm going to crib from the examples here to look up how to do this. So there's a good one in here. Transactions. You can see it has a similar structure, TX data. So this particular example is reading from the Farcaster storage registry. It's doing some encoding of the transaction and construction of the transaction. We'll just crib from that. So our Yoink contract is very simple, though. We're just making one simple call to a function that has no arguments, so we can avoid doing some of this setup. Okay, and here's the basic structure of a transaction route handler. So you're going to return JSON that looks pretty much like an Ethereum RPC request. Includes the chain ID, the method, so you can do signatures through frames as well. This is going to be just a transaction, but you could do ETH type signature v4, and then parameters that are, I think, pretty much identical to the JSON RPC call. Okay, so in our case, we're going to use the Yoink ABI. So yeah, we'll just pull in these constants that we defined in there. Oh, got to export it. We're going to call that contract address. Let's skip data for now. And no value with this transaction, so we're just going to need to construct the encoded call data to call the contract. All right, cool. So we can just use this VM helper. Encode function data. We can pass it the ABI of our contract, the function name that we want to encode, and get back the encoded call data to call a particular function on that contract. Oh, okay, and we need to change the change ID to base 8453. Okay, so that's our transaction handler. Our receipt handler is empty right now, but I think this will just work as it is. Let's give it a try. Famous last words. Reorder these buttons. Cool. So yeah, you can see the little lightning bolt here indicates that this is a transaction button. And hopefully if we're configured right, we can click this and something will happen. Sick, there we go. So yeah, this is prompting me in my connected wallet. You can connect up here in the Frames.js debugger, connect up to your own wallet here and trigger transactions. And yeah, you can see it simulated the transaction. We're transferring those tokens when I interact with it. Let's sign it. Cool. Okay, and then we've hit that that second route, right, that we defined. You can see we see the transaction receipt handler route, so that's returning the receipt handler frame. So we're not doing anything here yet, but this has received basically the transaction hash of that transaction, and we can use it to either watch the transaction and show like a loading state or show the user some feedback on what has happened. So let's build that out. So inside our context, when we're handling a transaction callback, we can access the transaction ID, which is just a generic name for like the transaction hash. We sort of designed this because we may do Solana transactions or other types of transactions in the future. So this is just, in the EVM context, this is just the transaction hash of the transaction that was triggered. And while we're at it, why don't we add like a base scan link in here as well? So we'll define Explorer URL. So this time we'll use a new action, a link. This is just a static link out to any URL. And we'll put that Explorer URL in here. Okay, ugly, but there it is, the transaction hash, and we can click out here and view the transaction on Basescan. Great, cool. So somebody's already playing Yoink on chain. That's great. I've yoinked it from someone else. So that's very useful because we have some rules in the game, right, that you can't yoink from yourself, and you have a timeout, right? So that's good. We haven't implemented handling those yet, so it might have reverted otherwise. Cool. Okay, yeah. So at this point, we kind of have a fully functional yoink game. You can see who's currently holding the flag. You can yoink it. You can trigger the transaction. It's a little bit ugly in that we are only showing Ethereum addresses, right, in our frames. Transaction hash, Ethereum address, rather than enhancing this with the data we can get from Farcaster, right? So we have this long, ugly Ethereum address has the flag. We would like that to be, if possible, right, a Farcaster username or some sort of more meaningful notion of user identity. So we can let's do that, yeah. We'll add some enhancements here to show the user's identity. So to do this, I'm going to use Nanar, which is an API for accessing Farcaster data. Our example here is sort of focused on building directly interacting on chains. We haven't made great use necessarily of Farcaster social context, right? We're not really reading the user's Farcaster ID in any of these frames here. We're sort of working in the other direction, right? We're going to go look because this game is on chain and figure out working back from their Ethereum identity to what their Farcaster identity is. So since we're running a little short on time, I'm going to grab these from the example repo. Okay, so we built out a few functions here. Let's just copy paste this. All right, we're pulling in the Nanar API client. This is going to give us access to this SDK that can give us information about Farcaster identity and sort of interactions with a bunch of different Farcaster-related APIs. We'll set up a client and have built out some utility functions here, right? So one of these lets us fetch Farcaster users by their associated Ethereum address. So we can use that basically to say when we have an address, let's convert it to a user. Let's not worry about this one for now. And then just a helper in here for truncating addresses, which are a little bit ugly. I think we have a special API key. If anyone else is building here too, you can use Nanar DevCon 2024. Okay, and yeah, going back to our start route here, let's enhance this with the user's actual identity rather than their blockchain address. Cool. Okay, so yeah, we grabbed that Ethereum address. We used the Nanar API to look up, batch lookup users who were associated with that address and their Farcaster identity, and got back a username here, rather than showing their on-chain address. You can see that was pretty slow, right? I think it's not just the network here, right? We're making like multiple async requests here to go make an RPC call to read on-chain data and to go out to the Nanar API and make an API call there. So we're probably like kind of at the limit of what this frame can handle in terms of the timeout if we want to keep it responsive. One thing we can do is, at the very least, is do that action concurrently, right? So we can use promise all or something to make that a little bit more performant. Okay, so yeah, final thing I think we may want to do in here is handle error cases from the contract. Which I think may be what's happening here. I've been timed out, right? So I recently called yoink with this address, but right now I've been rate limited, right? I can't yoink for another 10 minutes. So we're not handling that well right now, right? This is just crashing. So let's catch that custom error from the contract and display a nice message back to the user. Okay, so to do this, we're going to simulate the transaction first. We're going to see if it reverts, and if we catch an error from that revert, we're going to display it back to the user. All right, so we can use this helpful simulate contract function from VM to simulate the contract call. We'll just create a helper here. Let's import address. All right, and then here in our transaction call data generation handler, we will simulate the call. If we catch any errors from this, this is like pretty gnarly VM code for catching a custom error. But yeah, basically we walk these errors, anything that comes back. We'll catch the errors convert them from their on-chain representation, right? We have unauthorized, which is the error you'll get back if you already have the flag. And slow down, which is the custom error that you'll get if you're rate limited. And just convert these to nicer, more human readable errors. Okay, let's grab our functions here. Cool. So yeah, within a frame context, you have the ability to return an error to the user, which will sort of show up in a toast in most clients. So this is sort of useful for simple error handling cases. You can do this from transaction frames. You can do it from other types of frames as well, which will just show a quick human readable error rather than returning a whole frame for an error. All right, let's give this a try. Cool. All right, I was able to call it that time. I think my timeout has passed. Let's try it again. Cool, there it is. So yeah, you can see it's a little difficult to catch sometimes in the frames debugger, but yeah, here we've converted that error, right, from the on-chain, sort of difficult to read custom error, concise custom error, into something that a user can read. You have the flag, you can't yoink from yourself. And let's try out that rate limiting error as well. So I'll change addresses. Let's change back. Cool, and there's our second custom error. You're yoinking too fast, try again in 520 seconds. So we could convert that to a nice human readable date would be nice to do. But yeah, that's sort of the principle there. We're converting those on-chain, difficult to read on-chain errors into a nice human readable error message here. Okay, final step in here. I'm not going to implement it since we're running out of time, but let's just take a quick look at the code. So the last thing in here is to build out a leaderboard. And if you want to go, look at this separately, the idea here is that it's very difficult to build out a leaderboard in a performant way, right? We could load all the log data, like calculate how many people have yoinked and kind of do all those calculations within the context of the route. That's very difficult though, right? So it's a good example of where you should use an indexer or sort of caching to keep your frames performant. So there is an example in here of a really simple ponder indexer, which I built. So Ponder is a great open source tool for building indexers for Ethereum applications. You can sort of spin it up, point it at your contracts, and you get a really nice simple syntax for writing indexers. So I've set this up as sort of a separate API service here that we can use to read the leaderboard and read recent activity. And so if you're doing anything that kind of needs real-time data, right, or performant data, it's a good idea to use something like an indexer to load that. So go check that out in the repo. You can sort of see how to interact with that API, load the data from that API, and build out a leaderboard route. Okay, last step here. Let's look at the actual live app. So if you go to the repo and look at the code, this is the one that's deployed. And we'll put it all together and post this game. Cool. So this is the Warpcast debugger. This is kind of the final. Yep. All right, here we go. New yoink just dropped. Cool, and there's the final game. So go find that on Warpcast, check it out. Yeah, happy yoinking, everyone. Thank you.
Thank you so much, Horsefax, for the wonderful session on Farcaster frames. So we have a few questions here. So can I integrate frames to my existing site as a component, or is it, or it must be inside Farcaster?
Yeah, so I would look within frames.js is a good example of this. There are a couple tools for like embedding frames on the web. In fact, frame.js, you have a renderer, right, David? Yeah. So frame.js has a renderer tool, like a library that you can use to render frames outside of Farcaster context in like a general web context or other contexts. So the answer is probably yes, you can embed them in other applications.
Thank you.
Yep.
So let's thank the speaker.